All right, let's jump right in. Today, we're going deep on a pretty cool challenge in material science.
Oh, yeah.
Yeah. It's all about designing these lattice spring systems,
Yeah.
ones that are strong, A&D electrically conductive.
Sounds complicated.
It is, but the trick is to do all that without the costs getting out of hand.
Ah, the real world stuff. Makes sense.
Exactly. And this paper you sent over.
A dimension reduction procedure for the design of lattice spring systems with minimal fabrication cost and required multifunctional properties.
Yeah, that's the one. They
Okay.
really dive deep into optimizing those trade-offs.
Makarenkov, Malhotra, and Jiao, they even go all the way to a mathematical proof for their solution. It's impressive stuff. 2017 paper, updated in 24.
Okay, so before we get too lost in the math, though, can we set the scene a bit?
Sure.
Imagine we're designing some new material. It needs to handle force without getting permanently messed up. And Hambade needs to conduct electricity like a champ.
Right. And the way engineers think about this is with something called a lattice spring model.
So we're talking about a material that's basically a bunch of springs all hooked up together.
You got it. Each spring, you think of it like a component of the material. And the way they're connected, that determines how the whole thing behaves.
But these aren't your regular slinky springs, right?
Nope, not at all. These are what we call elastoplastic springs.
Fancy.
Well, they act like normal springs up to a point. Then they hit their elastic limit and bam, permanent deformation.
So like bending a paper clip too far, it doesn't spring back anymore.
Exactly. And that limit, knowing it, that's key. It tells us how much a material can take before it's damaged for good.
Okay, that makes sense. But how do we measure the strength of this whole springy material then?
They use this idea of response force. It's basically how much force the entire network of springs can handle before any one of them hits that limit and deforms, denoted by F.
So F is like the material's overall toughness.
Yeah.
But then there's cost too, right?
Can't forget about cost. And they define that, see, as the sum of all the elastic limits of each spring in the network.
So a higher cost basically means we've got stronger individual springs.
You could think of it that way. But it's not just about each spring being strong on its own, it's finding the best arrangement. We got to achieve the strength and the conductivity we need without spending a fortune.
Right. Because conductivity adds a whole other layer to this.
For sure. We have to factor in the material's resistance, R, and usually the thinner a spring is, the more resistance it has, doesn't conduct as well.
So it's like a balancing act. Strong strings for high response force, but not as so strong that they get thin and mess up the conductivity.
You've got it. That's the dance. Strength, conductivity, and cost. It's what makes this problem so interesting.
And the paper, they tackle it head on by looking at just FUR springs.
Yep, 4 springs. Sounds simple, right?
Definitely not what I expected.
But here's the thing. It lets them show off this technique called dimension reduction.
Dimension reduction.
Yeah.
Sounds a bit sci-fi.
Maybe a little, but it's basically a way to simplify. Instead of trying to optimize all 4 springs at once, they look at how the network acts under different conditions.
Like what happens if this spring hits its limit first, that kind of thing.
Exactly. And that lets them simplify the equations, focus on fewer variables. It's pretty smart.
So fewer variables, simpler problem, but still a lot going on. They analyze every possible way to arrange those 4 springs.
10 cases total, each a different configuration.
And the winner is?
Case 9. That's the arrangement with the lowest cost, and it still hits the targets for strength and conductivity. They prove it too, very elegantly.
Case 9, our champion. I'm ready to hear how they got there.
Me too. But first, I think we should break down how they actually calculate all this stuff. Response force, cost, resistance, for any given network.
Good point. Let's get into the nuts and bolts of the math. Visualize this. 2 springs, end-to-end a series connection. Now another pair, same deal. Then connect those 2 pairs, side by side, parallel. That's our 4-spring network.
Simple enough. So now how do we get the resistance, the R, for the whole thing?
Well, that's where the basic circuit rules come in. Series, parallel, all that.
Right. Series, you just add the resistances. Parallel gets a bit more tricky.
Okay, so we're applying basic circuit stuff to our springs. But what's the actual equation look like?
Let's say the elastic limits for our 4 springs are C1, C2, C3, and C4.
Okay, so we're using elastic limit as kind of a stand-in for both strengths and resistance.
Exactly. Higher elastic limit generally means stronger and more conductive.
Makes sense. Thinner springs, higher resistance, remember.
Right.
Yeah.
So for this setup, the total resistance R, it's calculated as R equals 1 divided by the quantity C1 plus 1 divided by the quantity C4 plus 1 divided by the quantity 1 over C2 plus 1 over C3.
Whoa, that's a mouthful.
I know, it looks intimidating, but bear with me. That innermost part, 1C2 plus 1C3, that's C2 and C3 combined, they're in series. Then we take 1 divided by that whole thing because they're in parallel with C4.
So it's all about carefully applying those series and parallel rules, step by step.
You got it. And that gives us R, the total resistance of our little network.
Okay, resistance check. What about response force, the F? How do we get that?
That's where things get a bit more interesting. Now we got to figure out which spring is going to hit its limit first. Which one's the weakest link, you know?
Right, because that'll determine the strength of the whole network. How do we find that weak link?
Well, for our example, we said C2 is less than C3. So in that C2, C3 pair, C2 is weaker. Now we got to compare C2 to C4.
We're narrowing it down.
And let's say C2 is weaker than C4 too. So most likely C2 is going to be our limit in that part of the network.
The bottleneck for strength. But what about C1? It's hanging out over there, parallel to that whole group.
Good catch. So now we compare C1 to the combined strength of the C2, C3, C4 group. And this is where we use this idea of equivalent elastic limits.
Equivalent.
Basically, we pretend C2 and C3 are one spring with an elastic limit of just C2. Since C2 is the weaker one, simplifies things.
So one imaginary spring instead of two real ones?
Exactly. Now, that imaginary spring with C2 as its limit, it's in parallel with C4. And since C2 is less than C4, the combined strength of those two is still limited by C2.
The weakest link still dominates. Now it all comes down to C1 versus C2.
Right. If C1 is stronger than C2, then the response force, F, for the whole network, that's just equal to C2.
Makes sense. Weakest link sets the limit. But what if C1 IS weaker than C2?
Then C1 becomes our new weakest link, and M would be equal to C1. So it's always about that smallest elastic limit among the important springs.
Got it. Okay. So we've got resistance, R, and response force, F. What about cost, C? That one seemed pretty straightforward.
You remember, just add up all the elastic limits in the network. So for our example, C equals C1 plus C2 plus C3 plus C4.
Easy peasy. So now we have our three key metrics, resistance, response force, and cost, all defined. And the goal is to minimize cost while still hitting specific targets for R and F.
Exactly. And that's where the paper's dimension reduction method really shines. By analyzing these cases, they can pinpoint that special configuration of springs our champion, case 9, the one with the lowest cost that still does what we need it to do.
And to think, this all started with just 4 little springs.
Amazing, isn't it?
I can't wait to hear how they proved that case 9 is the top dog. But I think we're going to have to save that for part 2 of this deep dive.
I think you're right. There's a lot more to unpack.
Okay, so we've got the basics down. How to figure out the resistance, the response force, and the cost for these lattice spring systems. Now let's get to the cool part, the optimization. How do they actually prove that case 9 is the best?
That's where dimension reduction comes in, right?
Yeah.
Remember, they've got 10 different setups for those 4 springs.
Yeah, 10 cases.
Right. And they got to find the one that keeps the cost down, but UT still hits the performance targets. Strength, A&D, conductivity.
It's a balancing act for sure. And they do this by kind of breaking the problem down into smaller pieces.
Right. Exactly. They don't try to optimize all 4 spring strengths at the same time. Instead, they look at how the whole network behaves under different situations, like which spring is going to hit its limit first.
Ah, so they're finding those weak links and using that to make the problem simpler.
You got it. That's where those cases come in. Each case is based on which spring or springs are likely to become plastic first. That tells you a lot about how the whole system is going to act.
Okay, so can you give me an example of one of these cases? Like, how do they actually define them?
Let's go back to that setup we talked about before. 2 pairs of springs in series, then connected in parallel. Remember we said C2 is less than C3?
Right, making C2 the weaker one in that pair.
Exactly. Now we got to compare C2 to C4, which is in parallel with the C2, C3 pair. And we're going to look at TWO scenarios here. One where C1, the spring, in parallel with the whole group, is weaker than the other 3 combined, and one where it's stronger.
Okay, so 2 separate cases based on how C1 compares to the rest.
Exactly. So in that first case, where C1 is the weakest link overall, meaning C1 is less than C2 plus C4. In this case, the response force, F, for the whole network is going to be limited by C1.
Because that weakest link, it sets the bar for the whole system.
Right. And then in the second case, where C1 is stronger than the other three combined, so C1 is greater than C2 plus C4, then the response force, F, it's going to be determined by that combined strength, C2 plus C4.
So we've got two cases, one where C1 calls the shots, and one where the C2, C3, C4 group sets the limit.
Exactly. And here's the brilliant part. The authors use these cases to simplify the problem down to just TWO variables.
Wait, TWO variables? We started with 4 spring strengths. How did they get rid of 2 of them?
It's a clever trick. Let's stick with case 1 for now, where C1 is the weakest link. Since KNOWC1 is going to hit its limit first, it means we can actually ignore C3 and C4 in our calculations.
Hold on, just ignore them, but they're part of the network.
I know, right? But think about it. C1 is the bottleneck. No matter how strong C3 and C4 are, the whole network strength is still limited by C1. So they basically replace C3 and C4 in the equations with expressions that only use C1 and C2.
So they're not really gone. They're just rewritten using C1 and C2.
Precisely. And they can do that because they've already figured out the relationships between all those variables specifically for case 1, and that gives them new simplified equations for the response force, F, and the cost, C. They call them F tilde at R and C tilde.
Okay, so they've gone from 4 variables down to 2 for case 1. What about case 2?
Same idea. In case 2, where the combined strength of C2, C3, and C4 is what matters, they eliminate C1 and C3, express them in terms of C2 and C4, and again, they end up with simplified equations, F tilde R and C tilde, now just depending on C2 and C4.
So 2 sets of simpler equations, one for each case. What happens next?
This is where it gets really cool. Visually, they plot these equations on a graph.
A graph. They're solving an engineering problem with a graph.
You bet. And by plotting those simplified equations, they can actually see the areas where the cost, the C tilde, is minimized while still meeting the requirements for strength A and D, that multifunctional performance, F tilde R.
So they're looking for that sweet spot. Lowest cost, but still enough strength and good performance, all shown right there on the graph.
Yep. And the amazing thing is, the best solution, the one for case 9, it's right on the border between those two cases. It's where both cases are satisfied at the same time.
So they found that perfect balance point.
Exactly. And that graph, it shows you the optimal values for all 4 springs, C1, C2, C3, and C4 for case 9.
I gotta say, this whole approach is really impressive. It's like they combine serious math with a really intuitive visual solution.
It's a bit like cracking a code, isn't it? They took this complex problem, broke it down into manageable pieces, and bam, the solution pops right out.
So they've shown that case 9 is the best out of those 2. But what about the other 8 configurations? Did they just skip those?
Not at all. They went through all the others, one by one, and showed that none of them could beat case 9 in terms of cost. And that's what we'll dive into in the last part. They did a very thorough job proving their solution.
Okay, so we've seen how they tackled those 2 cases, right? Found that case 9 was the best in those scenarios. But they didn't stop there, did they?
Oh, no, not at all. They went through each of the other 8 spring setups, the remaining cases.
To prove that none of them could beat case 9.
Exactly. They wanted to be absolutely sure. And for each one, they used that same dimension reduction strategy, simplifying, breaking it down.
So finding those key variables, like we saw before, to make the problem easier.
Yep. They wanted to get to a point where they could analyze it, visual A and D mathematically, to really see what was going on.
Can we walk through one of those other cases, just as an example?
Sure. Let's take case 1. In this one, all 4 springs are arranged so that they all contribute directly to the total resistance.
And remember, lower resistance is what we want for good conductivity.
Right. Now, for case 1, they use these inequalities, clever little mathematical tricks to simplify things.
Inequalities?
Yeah, they're like statements that compare things, like saying one value is greater than or less than another. And by using those, they could eliminate some of the variables based on the relationships between the elastic limits.
So fewer variables to worry about.
Exactly. And in the end, they got it down to just one variable, C1.
Wow, from 4 down to 1. That's pretty impressive.
It is. And once they had it down to one variable, they could plot it all on a graph. They had the cost, C, as a function of C1, and then they also had these constraint curves.
Constraint curves, what are those?
Those represent the requirements, the response force, F, and the multifunctional performance, FR.
Yeah.
They basically show you the boundaries of what's acceptable.
So the graph shows all the possible values for C1, but those curves tell you which ones actually work, which ones meet the requirements.
You got it. It's like they're mapping out all the good solutions, the ones that are feasible.
So what did they see on this graph for case 1?
Well, they saw that no matter what value you picked for C1, the cost, C, was always higher than what they got with case 9.
So visually, case 9 was still the winner.
Exactly. And they went through the same kind of process for all the other cases. Inequalities, substitutions, graphs.
Systematically knocking them all down, showing why case 9 was always better.
Yep. Sometimes they ended up with one variable, like in case 1. Sometimes it was 2 variables, like those cases we talked about before. But the result was always the same.
It's amazing how they mapped out all the possibilities for a four-spring system and found the absolute best one. Really impressive.
It really is, and I think there's a takeaway here for our listeners. Even problems that seem really complicated, like this material design stuff, they can often be broken down and simplified.
By using the right tools and the right approach.
Exactly. They showed us how to do that. Break a problem into smaller pieces, analyze each one, and then put it all back together to find the solution.
Now, this paper, they focused on 4 springs. What if we could scale this up? Like, imagine hundreds, thousands, even millions of elements.
Now you're talking. That's where this gets really exciting. Think about designing these intricate lattice structures with properties that are exactly what you need for a specific application.
So lighter materials for airplanes, or maybe materials that conduct electricity super well for electronics.
Exactly. And this paper, it lays the foundation for that. It shows us that it's possible to use this kind of approach, this dimension reduction, to tackle those bigger problems.
Well, this has been a fascinating deep dive. We've seen how researchers are using some serious math to push the boundaries of material design, and it all starts with something as simple as a spring.
It's true. Sometimes the most complex things have their roots in those fundamental ideas, and by understanding those basics and using a systematic approach, well, who knows what we can achieve.
I hope this deep dive has inspired you to look at the materials around you in a new light and to appreciate the power of math in driving innovation. Thanks for joining us. Welcome back, everyone, for another deep dive. This time, we're going to be focusing on materials science. More specifically, we'll be looking at a research paper that dives into how to design the most cost-effective lattice-spring systems, all while making sure they still have certain multifunctional properties.
You can think of it as, trying to find that sweet spot between keeping costs down and making sure the material actually performs the way you need it to.
Right. And the paper that's going to guide our deep dive today is called A Dimension Reduction Procedure for the Design of Lattice-Spring Systems with Minimal Fabrication Cost and Required Multifunctional Properties by Makarenkov, Malhotra, and Jiao. So before we get into the nitty-gritty, you might be thinking, why lattice-spring systems? What's so special about them? Well, these systems, they're incredibly versatile.
Oh, absolutely. I mean, you find them everywhere, from aerospace components to biomedical implants, you name it.
And if we can really figure out how to optimize their design, well, that could lead to some serious advancements in all those fields.
Oh, for sure. Think lighter but stronger aircraft components. Or, medical implants that are more compatible with the body and, just work better overall. That's what this paper's all about. It's about getting into the math behind all that.
Yeah, and that's what makes this paper so cool. It goes beyond just, the theoretical stuff. It gives you like an actual mathematical framework to actually optimize these systems. So are you ready to get into these equations and proofs and all that good stuff?
Let's do it. The paper, it starts off by introducing this concept called the elastoplastic lattice-spring model. It's kind of a fundamental thing to understand, before you can really dive into how these systems behave.
All right, so let's break that down a bit. The elastoplastic lattice-spring model, it basically looks at materials as like a bunch of interconnected springs, right?
Exactly. So each spring, you can think of it as a tiny segment of the material. And it can act in 2 ways. Elastically, where it, goes back to its original shape after it's stretched or whatever. And then there's plastically, where it permanently changes shape.
So like a rubber band versus like modeling clay or something.
Perfect analogy.
Yeah.
And this paper, it focuses on springs that are, elastoplastic. meaning they do both. So up to a certain point, they're elastic, then they kind of give way. And that point, that's called the elastic limit.
And that elastic limit, that's got to be super important, right? Because it basically determines how strong the material is overall.
Right. And the strength of the material, the paper, it calls it the response force, and they use the letter F for it. It tells you how much force the material can take before it permanently deforms.
So a higher F means a stronger material. Got it. But, how does cost factor into all this?
Well, the cost of the material, they use the letter C for that. It's directly tied to the elastic limits of all those little springs in the system. The paper defines it as like the sum of all those limits.
Okay, that makes sense. So just thinking off the top of my head, you might think, okay, to make it cheap, let's just use one really strong spring. But I have a feeling it's not that simple.
Yeah, you're on the right track. If you just used one spring, you'd end up with a material that's, strong in one direction, but weak in others. And, most of the time you need your material to be able to handle forces from different directions. We need multifunctionality.
And that's where things start to get really tricky. These researchers, they wanted a material that wasn't just strong, but could also conduct electricity really well. How did they even start to tackle that?
So what they did was they added these current conducting springs into their model. And just like in an electrical circuit, each spring has a certain resistance. They use the letter R for that. The lower the R, the better it conducts.
Okay, so now we've got two big things to think about. We've got the strength, represented by F, and the conductivity, represented by R.
Exactly. And what we're really trying to do is figure out, what's the lowest cost, C, while still making sure the material is strong enough and conducts well enough.
They call that combined measure multifunctional performance, or FR. And they even have a whole equation for it that combines F and R. And this is where the math starts to get really, really interesting.
Yeah, it definitely does. To make things a little easier, they decided to focus on systems that just have 4 springs. And there's a good reason for that. Previous research has shown that, when you have systems with 5 springs and you try to optimize them, you often end up with one of those springs having an elastic limit of 0. Which basically means it's useless. It's not even there. So it basically becomes a 4-spring system anyway.
So 4 springs is like the magic number for efficiency.
You could say that.
Okay, so now they've got these 4 springs. But how do they actually figure out the best way to arrange them? Did they just randomly try different combinations?
Well, they didn't just randomly test things out. They took a much more systematic approach. They looked at all these different arrangements, and for each one, they examined the equations for the resistance and the response force. And what they were really searching for was the arrangement that could give them the lowest possible cost while still meeting, those performance requirements.
Okay, so it's like a balancing act between cost and performance.
Huh.
Got it. And after looking at all those arrangements, did they find a clear winner?
They did. They identified one arrangement that really stood out as particularly promising. They called it Case 9.
Case 9. Okay, so tell me more about what this specific arrangement actually looks like.
Sure. So in Case 9, you've got 2 pairs of springs, and they're connected in parallel. And then those 2 pairs, they're connected in series with each other. So imagine 2 springs side by side, and then another 2 also side by side. And then you connect those 2 sets end to end.
Okay, yeah, I think I can picture that. So they've got this arrangement. But how did they actually, prove mathematically that this was the one that could, lead to the lowest cost?
Right. Well, that involved a fair amount of pretty intricate calculations. So remember, we got to consider both the resistance R and the response force F. Right. Let's start with the resistance calculation.
So how did they go about figuring that out?
Well, they use those, standard formulas for calculating the equivalent resistance, when you have resistors in series and parallel. So if you think back to that diagram of Case 9, we've got those 2 sets of parallel springs, and then they're connected in series.
Yeah,
right?
so it's kind of like calculating the total resistance in an electrical circuit.
Yeah, exactly. Yep. So for Case 9, that total resistance R, it's calculated as, well, it looks a little complicated when you write it out.
Let's hear it.
Okay, so it's R equals 1 divided by, in parentheses, C1 plus 1 divided by, again in parentheses, C4 plus 1 divided by, and one more set of parentheses here, 1 divided by C2 plus 1 divided by C3. And then you close all those parentheses.
Whoa, okay, yeah, that's a lot of fractions within fractions. But,
Yeah.
I mean, at the end of the day, it's just reflecting how those springs are connected, right?
Exactly, yeah. It's taking into account all those parallel and series connections to give you the total resistance of the whole system.
Got it. Okay, so that's resistance. What about the response force, Epha? I feel like that's got to be even more complicated.
Yeah, it was definitely a bit trickier to calculate. So for that, they had to really carefully analyze a bunch of different scenarios. Basically, depending on which spring or, which group of springs hit their elastic limit first.
So they had to figure out, like, which part of the system was going to, like, give first under stress.
Yeah, exactly. And to kind of simplify things, they introduced this idea of an equivalent spring. So they took those three springs, C2, C3, and C4, and they basically visualized them all as one single spring.
So, like, combining those three into, like, a super spring?
Exactly, yeah.
Yeah.
And they called the elastic limit of that equivalent spring C234. And then they could compare that C234 to the elastic limit of that remaining spring, C1.
So it's like comparing C1 to, like, the combined effect of C2, C3, and C4.
Right, exactly. And that comparison, it led to two possible scenarios. So the first one is, what happens if C1 is less than C234?
Meaning, like, that individual spring, C1, hits its limit before that combined effect of the other three.
Exactly. And in that case, the response force of the whole system, it would be limited by C1.
So C1 is the weakest link, basically.
Yeah, you got it. Then there's the second scenario where C1 is actually greater than C234. So in that case, it's the equivalent spring, that C234, that hits its limit first. And that's what limits the response force of the whole system.
Okay, so basically the response force, it all comes down to, like, which spring or which group of springs hits its limit first. It's like a race to see who permanently deforms first.
Perfect analogy, yeah. But okay, so now we have to actually calculate the value of that C234. So to do that, we got to look at how springs C2, C3, and C4, how they behave. And again, they use this idea of an equivalent spring. This time, they combined C2 and C3 into a single unit, and they called the elastic limit of that C23.
Okay, so more equivalent spring.
Yeah, you got it. Now, if C2 is less than C3, then C23 is just equal to C2. Because if you think about it, when you stretch the system, spring C2 is going to hit its limit first. So the combined response of C2 and C3, it's going to be limited by C2.
So, like, the weaker spring is going to dictate how strong that combination is.
Exactly. And in that case, that total elastic limit of that equivalent spring, C234, it's just going to be C23, which is the same as C2 plus C4. So C234 equals C2 plus C4, but only when C2 is less than C3.
Okay, so what happens when C2 is greater than C3?
Well, then C23 would just be equal to C3. And C234 would be equal to C3 plus C4. So they basically just repeated that same process, comparing those elastic limits of individual springs and their equivalent combinations.
Sounds like a very, like, systematic and thorough approach. They really covered all their bases, didn't they?
Yeah, they did. They considered all those different combinations of C1, C2, C3, and C4. And for each one, they figured out the response force based on, which spring or equivalent spring hit its limit first.
All right, so they've got the resistance, they've got the response force for case 9. But how did they actually use all that info to, to actually minimize the cost? Did they just, like, plug those values into a formula or something?
Well, not quite. That's where their pretty ingenious dimension reduction technique comes in. So remember, the ultimate goal is to find the values of C1, C2, C3, and C4 that give you the lowest possible cost, C. But at the same time, you got to make sure the material still performs the way you need it to.
Right. So minimize cost without sacrificing that strength and conductivity. Find that sweet spot.
Exactly. But to find that sweet spot, they needed to find a way to, like, simplify the problem a bit. And what they realized was they could actually express both that multifunctional performance, FR, and the cost, C, in terms of just 2 variables instead of 4.
Wait, hold on. How did they manage to, like, reduce the number of variables? That sounds like some serious mathematical wizardry.
It was pretty clever. They took a close look at those equations for FR and C, and what they realized was they could actually eliminate 2 of the variables by applying some inequalities and making a few key observations.
Inequalities, like those greater than and less than symbols.
Yep, exactly. So, for example, in case 9, they knew that under certain conditions, C2 was going to be less than C3. So they used that inequality to basically replace any terms that involved C3 with terms that involved C2. So essentially, they were replacing a larger value with a smaller value in the equation.
So they were, like, strategically simplifying the equations without actually changing what they meant.
Exactly. And they kept doing that, using inequalities to get rid of variables until they were left with expressions for FR and C that only involved two variables.
Okay, I'm starting to see how clever this is. But why was it so important to reduce the number of variables?
Because it let them visualize the problem in a completely different way. So instead of trying to solve like this super complex system of equations with four variables, they could now plot the relationship between cost and performance on a simple two-dimensional graph.
Oh, so it's like turning this like multi-dimensional problem into something that we can actually see and wrap our heads around.
Exactly. And by looking at that graph, they could easily see which values would give them the lowest cost while still meeting those performance requirements.
So it's all about finding that optimal point on the graph where cost and performance like intersect.
You got it. And this approach, it worked perfectly for both of those subcases within case 9. They just, they used that same dimension reduction technique, inequalities, get rid of variables, and then they visualized it all graphically.
It's amazing how they took this like really complex optimization problem and turned it into this like more manageable visual puzzle.
Yeah, it really is. And it let them prove, without a doubt, that case 9 was the most cost-effective way to arrange those springs and get those specific multifunctional properties.
This is fascinating. But they didn't just stop at case 9, did they? I mean, they still had to look at all those other possible arrangements,
Yeah.
right? Just to be absolutely sure that case 9 was the real deal. So they went through and analyzed all those other possible arrangements. How many other arrangements were there? And like, how did they even approach what seems like a pretty big task?
Yeah, it was quite the undertaking for sure. So when you consider both series and parallel connections, there are actually 16 different distinct arrangements that you can make with 4 springs.
16. Okay, so yeah, that's a lot of different configurations to analyze.
Yeah, it's a lot. But they had a pretty structured approach. It was very similar to the process they used for case 9.
So it was like case 9 had to go up against all these challengers.
Yeah, exactly. So for each of these 16 cases, the first thing they had to do was figure out that equivalent resistance. And for that, they used those same standard formulas for resistors connected in series and parallel, like we talked about for case 9.
Okay, so that part was at least conceptually fairly straightforward.
Yeah, the resistance calculations were pretty systematic, but figuring out the response force for each arrangement, that was definitely the more challenging part.
Because of those elastoplastic springs and how, they can behave in those two different ways.
Exactly. So for each and every case, they had to very carefully go through and analyze all these different scenarios, right? They had to figure out which spring or, which combination of springs would hit their elastic limit first. And then, based on that weakest link, they could calculate the response force.
It sounds incredibly tedious, honestly, like
Yeah.
super complex. Did they have any like tricks or shortcuts to make that process a little more manageable?
Well, they did use a few clever strategies. So wherever they could, they used that dimension reduction technique, using inequalities to simplify the equations and reduce the number of variables.
So those same mathematical insights that they used for case 9, they were able to apply those to the other arrangements as well.
Exactly. They were always looking for ways to, streamline the process, but without sacrificing that accuracy. And in some cases, they were even able to reduce the problem down to just a single variable, which, obviously made the analysis a lot easier.
That must have been nice. So once they had the resistance and the response force for each case, did they just compare those values back to what they got for case 9?
Exactly. So for each case, they carefully compared the cost and the performance metrics to case 9, which was kind of the reigning champion.
And were there any close calls? Or was case 9 the clear winner from the beginning?
Well, even after going through and analyzing all 16 arrangements, none of them could beat case 9. None of the other configurations could give them a lower cost while still keeping that same level of multifunctional performance.
So case 9 really was the champion. Their hunch, backed up by all that hardcore math, it turned out to be right.
Yeah, absolutely. It really shows you how powerful a systematic, mathematically driven approach can be when you're trying to optimize something.
Well, this deep dive has been super insightful. We've gotten to explore all the ins and outs of the elastoplastic lattice-spring model. We went through all those calculations for resistance and response force, and we even got to see how clever math techniques like that dimension reduction thing can really make these complex problems so much easier to understand.
And, maybe most importantly, we've seen how, really thoroughly analyzing a problem and testing out all the possibilities, how that can lead to, finding solutions that are truly optimal.
Yeah, this research has definitely opened up some really exciting possibilities when it comes to, designing materials in the future. I mean, who knows what kinds of advancements we might see as we keep, exploring these techniques and refining them.
Oh, yeah, the potential applications are huge. We could be talking about, aircraft components that are even lighter and stronger, or, medical implants that are even more compatible with the body and just, function better overall.
It's amazing to think that these, seemingly simple springs could hold the key to such groundbreaking innovations.
It is. It just goes to show you how important fundamental research is and how powerful mathematical modeling can be when it comes to, driving technological progress.
Well, this has been a truly enlightening deep dive. Until next time, everyone, keep exploring, keep pushing those boundaries of knowledge, and remember, never underestimate the power of a well-placed spring. All right, let's dive into material science and optimization today.
Sounds good.
We're going to be looking at designing lattice spring systems
Okay.
that are strong and multifunctional, but we want them to be cost-effective too.
Right.
And we've got this paper here, a dimension reduction procedure for the design of lattice spring systems with minimal fabrication cost and required multifunctional properties.
Okay.
It's by Makarenkov, Malhotra, and Jiao.
All right.
We're going to unpack this complex problem and see how they use math to find the most efficient design.
Yeah, it's really fascinating how they tackle this real-world problem, designing these materials that can handle stress and conduct electricity,
Right.
but also, be produced affordably.
Yeah, absolutely.
It's a challenge that has implications for a lot of different fields.
For sure. So let's start with the basics.
Okay.
They use a lattice of springs to model these materials.
Right.
Can you explain why they do that and how it works?
So imagine a material as a network of interconnected points, and each point represents a tiny part of the material, and the connections between them represent how they interact when they're under stress. Now, replace those connections with springs.
Okay.
The stiffness of each spring
Yeah.
represents how much force it takes to stretch or compress that part of the material.
So it's kind of a simplified way to represent the material's internal structure
Yeah,
and how it responds to force.
exactly.
But these aren't your average springs, are they?
No, not at all.
They have some special properties.
They're elastoplastic,
Okay.
which means they behave elastically, like a rubber band,
Okay.
but they can also deform permanently
Okay.
if they're stretched too far, like clay.
So they can bend and snap back,
Right.
but if you push them too hard, they'll change shape for good.
Exactly.
That's pretty cool.
Yeah.
But why do they need to be electrically conductive?
Well, that's where the multifunctionality comes in.
Yeah.
Imagine materials that can withstand stress, but also conduct electricity. This opens up possibilities for creating things like flexible electronics,
Wow.
self-sensing structures,
Okay.
or even materials that can repair themselves by rerouting electrical currents.
That's incredible.
Yeah, it is pretty amazing.
But I can see how adding this extra requirement would make the design problem even more complex.
It does, yeah.
Yeah.
No, you're not just trying to find the strongest or most flexible arrangement of springs.
Right.
You also need to optimize for electrical conductivity.
Mm-hmm.
And of course, you want to do all of this while keeping the cost as low as possible.
Right, because in the real world, budget always plays a role.
Always.
So
Yeah.
how do they define cost in this context?
They define it as the sum of the elastic limits
Okay.
of all the springs in the system.
Okay.
So the elastic limit is essentially the point where the spring stops behaving elastically
Okay.
and starts to deform permanently.
So a higher elastic limit means a stronger spring,
Yes,
but also a higher cost.
precisely. And here's where it gets even more interesting.
Okay.
There's a direct relationship between the elastic limit of a spring and its electrical resistance.
Interesting.
They use the equation Re equals 1 over C,
Okay.
where Re is the resistance of the ith spring,
Hmm.
and she is its elastic limit.
So if you increase the elastic limit to make a spring stronger, you also decrease its resistance,
Exactly.
making it a better conductor.
Yes, so you can see the dilemma.
Yeah.
To minimize cost, You want to use springs with lower elastic limits.
Okay.
But to maximize conductivity, you want springs with higher elastic limits.
Right.
It's a balancing act.
It's a tough problem.
It is.
Now, can we go back to the elastoplastic behavior for a second?
Sure.
I think it would help to have a more concrete example.
Absolutely.
Yeah.
Think of a paper clip.
Okay.
You bend it a little and it springs back to its original shape.
Right.
That's the elastic behavior.
Okay.
But if you bend it too far, it stays bent.
Yeah.
That's the plastic deformation. The point where it transitions from elastic to plastic, that's its elastic limit.
Okay. That makes a lot of sense.
Good.
Now, I know they use a technique called dimension reduction
Right.
to tackle this optimization problem.
Yes.
Can you explain what that is and why they use it?
Well, optimizing a system with a large number of variables can be computationally very challenging.
Yeah.
Imagine trying to find the perfect combination of spring strengths
Okay.
for a system with hundreds or even thousands of springs.
Yeah, that sounds like a nightmare.
It would be. It would be.
Yeah.
So what they do is simplify the problem by reducing the number of variables.
Okay.
They focus on systems with only 4 springs.
Okay.
This makes the problem mathematically manageable
Oh,
while still capturing the essential features of the optimization challenge.
So it's like zooming in on a smaller piece of the puzzle,
Yeah,
but one that still represents the bigger picture.
that's a great way to put it.
Okay.
And the choice of 4 springs wasn't arbitrary. Previous research indicated that this specific number of springs could lead to an optimal solution.
Interesting.
Yeah.
So they're building on previous work
They are.
and focusing their efforts on a specific area that's likely to yield the best results.
Precisely.
Okay.
Now, even with just 4 springs, there are still many ways to arrange them.
Right.
The paper explores 10 different cases,
Okay.
each with a unique configuration of these springs.
So they're systematically exploring different possible layouts
Yes.
to see which one gives them the best balance of strength, conductivity, and cost.
Exactly.
Right.
And the paper dives deep into each case, analyzing the electrical resistance, response force, and cost for each arrangement.
Yeah.
But they pay particular attention to case 9, which
Right.
they believe holds the key to the most cost-effective design.
All right. I'm ready to unpack case 9.
Okay.
What makes this arrangement so special?
In case 9, the 4 springs are arranged in a specific way. Imagine 2 springs connected in parallel in the middle,
Okay.
with one spring attached to the top of those, but another to the bottom.
Okay. I can picture that.
Yeah.
It's like a slightly lopsided H shape.
That's a great way to visualize it.
Okay.
Now, to understand why this arrangement is so effective, we need to delve into how they calculate the electrical resistance
Okay.
and the response force of the system.
All right. Let's dive in.
Okay.
Starting with the resistance calculation. How do they account for the different ways the springs are connected?
They use a combination of basic circuit principles
Okay.
for series and parallel connections.
Okay.
Remember, the total resistance of springs connected in series
Yeah.
is simply the sum of their individual resistance.
Right. That's straightforward.
Yeah,
But for parallel connections, it gets a bit more complex.
it does, yeah.
Yeah.
For springs connected in parallel, the reciprocal of the total resistance is equal to the sum of the reciprocals of the individual resistances.
Okay, so they're using these principles to calculate the overall resistance of the case 9 arrangement,
Yes,
taking into account both the series and parallel connections of the springs.
precisely. They provide a detailed equation for this calculation in the paper.
Okay.
Equation 6,
All right.
which clearly shows how they factor in the individual resistances of each spring and the specific configuration of the arrangement.
Can you walk me through how they apply that equation to this specific case?
Certainly.
What parts of the H are in series and which are in parallel?
So in case 9 spring, 1 is in series with the combination of springs 2, 3, and 4.
Okay.
Springs 2 and 3 are connected in parallel,
Okay.
and then that combination is in series with spring 4.
Okay, I'm seeing it now.
Yeah.
So the equation takes into account the resistance of spring 1 plus the combined resistance of the other 3,
Yes.
considering their parallel and series connections.
Exactly.
Right.
This approach allows them to calculate the overall electrical resistance of the system based on the individual properties of each spring and their specific arrangement in case 9.
Okay, I'm following so far.
Good.
So they've tackled the resistance calculation.
Right.
What's next?
Now comes the analysis of the response force.
Okay.
This is where things get really interesting.
Okay.
To simplify the analysis, they introduce the concept of an equivalent spring.
Hold on. An equivalent spring.
Yes.
Can you explain what that is
Of course.
and how it helps?
So instead of dealing with the complexities of 3 springs connected in different ways, they replace springs 2, 3, and 4 with a single hypothetical spring that represents their combined behavior. This equivalent spring has an elastic limit that represents the overall strength of those 3 springs together.
Okay, so it's like compressing that lower part of the H into a single, more manageable unit for analysis.
Yes, that's a great way to think about it.
But doesn't that risk oversimplifying things?
It's a valid concern, but the researchers have carefully accounted for this simplification. The elastic limit of the equivalent spring is calculated in a way that accurately reflects the combined strength of the 3 original springs, considering their series and parallel connections.
So they're not just throwing away information.
No.
They're consolidating it in a way that still captures the crucial details of how those 3 springs contribute to the overall strength of the system.
Precisely. And this simplification allows them to analyze the response force of the system in a more systematic and manageable way.
I'm intrigued.
Good.
How does this equivalent spring concept help them analyze the response force?
With the equivalent spring in place, the system essentially boils down to 2 springs, spring 1, and the equivalent spring representing springs 2, 3, and 4.
So they've taken a 4-spring system and reduced it to a 2-spring system for the purpose of this analysis.
Exactly.
That's clever.
It is a clever approach. Now they need to consider different scenarios based on the relative strengths of these 2 springs. What happens if spring 1 reaches its elastic limit before the equivalent spring? What happens if the equivalent spring reaches its limit first?
Because depending on which spring gives first, the overall response force of the system will be different.
Exactly. And the paper meticulously analyzes 4 different cases, represented by equations 7 through 11, to determine the response force under these various scenarios.
So they're essentially figuring out how much force the system can withstand before it starts to permanently deform. Based on the individual strengths of the springs and which one reaches its limit first.
Precisely. This detailed analysis of the response force, along with the earlier resistance calculation, lays the groundwork for the optimization process.
All right, I think we've covered a lot of ground here. Let's take a moment to recap before we dive into the next stage. We started by understanding why they're using elastoplastic current-conducting springs to model these materials and how cost is defined in this context. Then we explored the specific arrangement of springs in case 9.
We did.
Visually imagining it as a slightly lopsided H.
Yes, a good visual.
And then we delved into the detailed calculations for electrical resistance.
We did.
Highlighting how they factored in both series and parallel connections of the springs. Then we introduced the concept of an equivalent spring. Simplifying the system for the response force analysis.
Exactly.
And they meticulously analyzed 4 different cases based on the relative strengths of the springs.
They did.
To determine how much force the system can handle before permanent deformation.
Yes, very thorough.
So with all of this groundwork laid, where do we go from here?
Now comes the exciting part. The actual optimization process. They've set the stage, and now they need to figure out the exact combination of spring strengths that will give them the lowest possible cost while still meeting the required strength and conductivity targets.
I'm ready to see how they tackle this optimization challenge.
Let's get into it. Let's begin by understanding how they reduce the problem even further. Remember, even with just 4 springs, finding the optimal solution could still be a computational challenge.
We talked about dimension reduction earlier, but I'm guessing they take it a step further here.
Exactly. They make a strategic assumption. They focus on the scenario where the elastic limit of spring 2 is less than the elastic limit of spring 3.
So they're essentially saying, let's assume that spring 2 is weaker than spring 3.
Yes.
Why is that assumption helpful?
This assumption allows them to eliminate a significant portion of the possible solutions that wouldn't be optimal anyway.
So by making this one assumption, they streamline the search for the optimal solution.
Precisely. And the beauty of it is that this assumption doesn't sacrifice the accuracy of their findings. It simply focuses their efforts on the most promising area of the solution space.
Okay, I'm starting to see how this all fits together.
Good.
But how does this assumption translate into a reduction in the number of variables?
Okay, so
We were dealing with 4 springs initially,
right.
and now we have this equivalent spring. Where do we stand?
With this assumption in place, they can now express the optimization problem in terms of just 2 variables.
Okay.
The elastic limits of springs 1 and 2.
Wow, so they've gone from 4 springs down to 2.
Yes.
That's a significant reduction in complexity.
Absolutely. And this reduction makes the problem much more manageable from a mathematical and computational standpoint.
Yeah.
They present these 2 variable estimates for both the multifunctional performance and the cost in Table 2 of the paper.
Okay, so Table 2 is essentially a summary of the key parameters
Yes.
they're working with after applying this dimension reduction technique.
Exactly. And it's important to note that they further refine the analysis by breaking down case 9 into 2 subcases.
Hold on, subcases.
Yes.
Why the need for further division?
These subcases distinguish between the scenarios where spring 1 reaches its elastic limit before the equivalent spring,
Okay.
which is case 9.1,
Okay.
and vice versa, which is case 9.2.
Okay, so they're essentially saying we need to consider both possibilities.
Yes.
Spring, one failing first, or the equivalent spring failing first.
Exactly.
And each possibility leads to a slightly different optimization problem.
Exactly. This meticulous approach ensures that they cover all the bases
Okay.
and arrive at the most accurate and comprehensive solution.
All right, so they've simplified the problem,
Right.
made a key assumption, and broken it down into subcases.
They have.
What's the next step in this optimization journey?
Now they bring in a powerful tool,
Okay.
visualization.
Go.
They use a graph to represent the optimization problem and its solution. This graph, shown in Figure 1 of the paper, is key to understanding how they arrive at the optimal combination of spring strengths.
Okay. I'm ready to see how they put this visual representation to work. Take me through it.
Imagine a graph where the horizontal axis represents the elastic limit of spring 1, C1,
Right.
and the vertical axis represents the elastic limit of spring 2, C2.
Okay.
Each point on this graph represents a possible combination of spring strengths for the system.
Okay, so every point on the graph corresponds to a specific design for the Lattice-Spring system.
Precisely. Now remember their goal.
Right.
To find the combination of spring strength that minimizes cost.
Yes.
While still meeting the requirements for strength and conductivity.
Okay.
They represent these requirements as constraints on the graph.
So are these constraints like boundaries on the graph?
Exactly.
Limiting the area of possible solutions?
Exactly. The strength constraint might say, for example,
Okay.
that the system needs to withstand a certain minimum force before deforming permanently. And the conductivity constraint might specify a minimum level of electrical conductivity.
Yeah.
These constraints create a feasible region on the graph,
Okay.
the area where all the requirements are met.
So they're essentially narrowing down the possibilities
Yes.
to the area on the graph where the system is both strong enough and conductive enough.
Precisely now within that feasible region.
Okay.
They need to find the point that represents the lowest possible cost.
So it's like they're searching for a needle in a haystack.
Yeah.
But the haystack is now a much smaller, more manageable area on the graph.
That's a great analogy.
Right.
And to find that needle, they use lines of constant cost.
Okay.
These lines represent different cost values.
Okay.
And they're plotted on the graph as well.
So each line on the graph represents a different level of cost.
Yes.
Like contour lines on a topographic map.
Exactly. And just like with contour lines, the closer the lines are to each other,
Okay.
the steeper the change in cost.
Okay, I'm picturing it now.
Yeah.
So how do they use these lines to pinpoint the optimal solution?
They look for the lowest cost line that still intersects the feasible region.
Okay.
The point where that line touches the boundary of the feasible region.
Okay.
That's the sweet spot,
Okay.
the optimal solution.
So it's the point on the graph
Yes.
that represents the lowest possible cost while still meeting all the strength and conductivity requirements.
Exactly.
Elegant.
It is a very elegant solution.
Yeah.
And to back up this graphical solution,
Yeah.
they provide the mathematical proof.
Okay.
This is where Proposition 1 in the paper comes in.
Okay. Tell me about this Proposition 1. What does it prove?
Proposition 1 essentially demonstrates that if you can find the optimal solution for the reduced 2-variable problem,
Okay.
that solution will also be the optimal solution for the full 4-variable problem.
So solving the simplified version of the problem is enough to solve the whole thing.
Absolutely. It's like finding a shortcut through a maze.
That's pretty powerful.
It is a very powerful result.
Yeah.
And this proposition is backed up by rigorous mathematical reasoning. ensuring the validity of their findings.
Okay, so they visualized the problem, identify the feasible region,
Right?
use caught lines to pinpoint the optimal solution,
Yes.
and backed it up with mathematical proof.
They have. It's a very comprehensive approach.
That's a comprehensive approach.
Yep.
But do they give us any concrete numbers?
They do.
What are the actual values for the spring strengths in this optimal solution?
Equations 15 and 16 in the paper present the optimal values for the elastic limits of all 4 springs, along with the minimum cost achieved.
Fantastic. So we have the visual representation, the mathematical proof, and the numerical solution.
We do.
This case 9 is shaping up to be quite the contender.
It is, and the paper goes even further,
Okay.
analyzing the other 9 cases to prove that none of them can achieve a lower cost than case 9.
Okay, before we dive into those other cases,
Sure.
can you give me a high-level overview of how they approach analyzing them?
Okay.
Do they follow a similar pattern to case 9?
They do. For each case, they start with the specific arrangement of springs, calculate the total resistance, and analyze the response force.
Okay.
Then they apply dimension reduction techniques,
Oh.
often making strategic assumptions based on the structure of the problem.
So they tailor their approach to the specific details of each case,
Exactly.
using similar principles but adapting them as needed.
Precisely.
Yeah.
And for each case, they aim to simplify the problem as much as possible,
Okay.
often reducing it to a single variable or 2 variable optimization problem.
Okay.
Then they use tables and graphs to visualize the solutions
Right.
and compare them to the benchmarks set by case 9.
All right. I'm ready to explore these other cases and see how they stack up against the champion. Let's get to it.
Now, diving into the details of these other cases might seem tedious,
Yeah.
but it's crucial to understand why they went through the trouble of analyzing each one.
You're right. It's like they needed to rule out all other possibilities
Yeah,
to definitively prove that case 9 is the champion.
exactly. So let's take a quick tour of the remaining cases,
Okay.
focusing on the key takeaways
Right.
without getting bogged down in too much detail.
Sounds good.
Yeah.
Let's start with case 1 again.
Okay.
We talked about how it's a simple series configuration,
Right.
but I'm curious about the specific limitations
Yeah.
that make it less cost-effective than case 9.
In a purely series connection,
Mm-hmm.
the overall strength of the system is limited by the weakest spring.
Okay.
If one spring fails, the whole system fails.
Right.
This means you need stronger
Yeah.
and therefore more expensive springs to achieve the desired strength.
So it's like a chain
Yeah,
where its strength is only as strong as its weakest link.
exactly.
That makes sense. What about case 2? Where all 4 springs are directly connected in series.
Right.
Does it have similar limitations?
Yes. Case 2 suffers from the same fundamental drawback of a series connection.
Okay.
The reliance on the weakest spring drives up the overall cost.
Okay, so those purely series connections are out.
Right.
What about case 3?
Okay.
Where we had those 2 pairs of springs in parallel. And then those pairs connected in series.
Yes,
I remember it was a single variable optimization problem.
it was.
What insights did they gain from analyzing that arrangement?
Case 3 introduced the concept of parallel connections,
Okay.
which can offer some advantages
Okay.
in terms of distributing the load and potentially reducing the reliance on the weakest spring.
Okay.
However, the
Yeah.
specific configuration in case 3, with those pairs of parallel springs then connected in series,
Right.
still didn't achieve the optimal balance that we see in case 9.
Interesting. So it's not just about having parallel connections.
No.
It's about the specific way those parallel connections are integrated into the overall structure.
Exactly, and that's what makes the analysis of these different cases so valuable.
Right.
It allows you to see how subtle changes in the configuration
Yeah.
can have a significant impact on the overall performance and cost.
All right, let's move on to case 4,
Okay.
where they had 3 springs in series connected in parallel with a 4th spring. This was a 2-variable problem, right?
Yes, it was.
Right.
And analyzing case 4 highlighted the challenges of working with more complex combinations
Okay.
of series and parallel connections. Even though they were able to reduce it to 2 variables,
Yeah.
the optimization process becomes more intricate when you have this interplay between multiple parallel branches
Right.
and series connections within those branches.
So it's like adding layers of complexity to the optimization puzzle,
Yes,
which makes it harder to find that perfect solution.
precisely. And cases 5 and 6 further demonstrate this point.
Okay.
They both involve more elaborate combinations of series and parallel connections,
Yeah.
requiring 2 variables for optimization in case 5
Okay.
and 1 variable in case 6.
And I'm guessing the key takeaway is that even with these more intricate arrangements,
Yes.
the optimal costs were still higher than what they achieved with case 9.
You are absolutely right. The analysis of cases 4, 5, and 6 shows that complexity doesn't necessarily equate to cost-effectiveness.
Okay, that makes sense. Sometimes a simpler, more strategic approach can be more effective.
Exactly, and that's what we see with case 9.
Right.
It's not the most complex arrangement, but it strikes the perfect balance.
All right, let's quickly touch on the last 3 cases. Cases 7, 8, and 10.
Okay.
Case 7 had those 2 pairs of springs connected in series and then in parallel.
Right.
Case 8 was the purely parallel connection.
Yes.
And case 10 was that elaborate multi-layered combination.
Yes, and the analysis of these cases further reinforced the findings from the previous ones.
Okay.
Case 7, with its combination of series and parallel connections, couldn't match the cost-effectiveness of case 9.
Okay.
Case 8, despite its simplicity, also fell short.
Yeah.
And even case 10, with its intricate configuration, couldn't outperform the champion.
So it's a clean sweep for case 9.
It is.
It really highlights the importance of that specific arrangement.
Right.
And its unique blend of series and parallel connections.
It does, and it's important to remember that the researchers didn't just rely on visual inspection or intuition to determine that case 9 was optimal.
Yeah.
They backed up their findings with rigorous mathematical analysis and optimization techniques.
Right. We talked about the visualization using the graph,
Yes.
the cost lines, and the mathematical proof.
Exactly, and they applied similar rigor to the analysis of the other 9 cases,
Okay.
ensuring a fair and comprehensive comparison.
Okay, so we've explored the ins and outs of this paper,
We have.
delving into the specific details of each case.
Yes.
And understanding why case 9 emerges as the most cost-effective design.
Right.
It's been a fascinating journey through the world of material science and optimization.
It has been a very interesting exploration.
Yeah, absolutely.
Yeah.
I think the key takeaway here is that mathematical modeling and optimization techniques
Yes.
are powerful tools for designing materials with tailored properties.
Absolutely. By carefully analyzing the arrangement and properties of individual components, we can create materials that are not only functional,
Right.
but also surprisingly affordable.
Absolutely. This research opens up exciting new possibilities for material design
Yeah.
across a wide range of industries.
It does. It's very exciting work.
It's truly a testament to the power of combining mathematical insight with engineering ingenuity.
Absolutely. A great example of that.
If this deep dive into the world of cutting-edge material science has sparked your curiosity,
Yeah.
I encourage you to explore the full paper and see what other insights you can uncover.
That's a great idea. There's a lot more to discover in the paper.
And until next time, keep on learning and keep on diving deep. Welcome to our deep dive today. We're going to get into some cost-effective design for lattice-spring systems.
Oh, that sounds interesting.
We've got this paper here. It's called a dimension reduction procedure for the design of lattice-spring systems with minimal fabrication cost and required multifunctional properties.
Okay.
And it's going to take us on a little journey into this world of topology optimization.
Oh, wait.
So first things first. When we're talking about lattice-spring models, we're talking about a network of springs.
Springs.
They're all connected at points called nodes.
Right.
But these aren't just any ordinary springs.
Okay, so not like the ones in my mattress.
Not quite, no.
Yeah.
These springs can either be elastic, meaning they bounce back to their original shape,
Right.
or they're elastoplastic, which means they deform permanently after a certain point.
Okay, so like after you stretch them too far,
Exactly, yeah.
they stay that way.
They say stretched out. And the type of spring that's used in this lattice is really important. It impacts both the strength and the conductivity of the system as a whole.
Oh, okay, so the type of spring affects how strong the whole system is.
Absolutely, yeah.
Yeah.
And how well it conducts electricity.
Huh.
And so this paper is really looking at how we can design these systems to be as strong and efficient as possible,
Okay.
but also how we can do that while keeping costs down.
Right, so balancing those two, getting the best performance without breaking the bank.
Exactly. It's a delicate balancing act.
Yeah, I can see how that'd be tricky.
And what's actually really fascinating is the paper highlights that sometimes the most cost-effective designs actually use springs with zero elastic limit.
Zero elastic limit, so they just like permanently deform under stress.
Yeah, that's right.
I mean, that kind of sounds counterintuitive, doesn't it?
Yeah, it does seem a little strange at first.
So how can that be the most cost-effective?
Well, it's all about thinking about the bigger picture, right?
Mm-hmm.
So The paper looks at 10 different arrangements of 4 springs.
10 different arrangements.
And through a bunch of simulations,
Yeah.
they actually found that the optimal designs, the best performing ones, often had some of these springs with 0 elastic limit. So it really kind of led them to dig into like the nitty-gritty math of these 4 spring systems.
Okay.
To see what was going on there.
Got it.
So out of those 10 cases, which one came out on top as far as, being the most cost effective?
Well, the winner was case 9.
Case 9. Okay. So help me to visualize that setup. What does that arrangement actually look like?
Okay, so imagine you have 2 springs connected end to end. So that's like a series connection. Now, picture another spring running parallel to those 2.
Okay, I'm with you so far.
And then this whole setup is connected in series to one more spring.
Got it.
So you've got this combination of series and parallel connections with these 4 springs.
And that specific placement, that arrangement, that's really important.
Exactly, because the way they're connected directly affects how strong and conductive the system is. To really understand it, you need to look at how electrical resistance is calculated in this setup.
Right, so let's talk about resistance. That's basically just how much a material resists the flow of electricity.
Yeah, that's the gist of it. And the way the springs are connected in case 9 determines the total resistance. We use those standard formulas for parallel and series resistances.
Can you refresh our memories on those formulas just so we're all on the same page?
Sure. So for springs in series, the resistances just add up. If you have 2 springs with resistances R1 and R2, the total resistance is just R1 plus R2.
Okay, that's pretty straightforward.
Yeah. But for parallel connections, it gets a little trickier. You have to do 1 divided by the total resistance, and that equals 1 divided by R1 plus 1 divided by R2.
Right. So in case 9, with its mix of series and parallel connections, we have to use a combination of those formulas to figure out the total resistance.
Exactly. You combine them depending on how the springs are arranged.
Makes sense.
And here's where the paper gets really interesting. It assumes that the resistance of each spring is inversely proportional to its elastic limit.
Wait, so a spring with a higher elastic limit, meaning it's stronger, actually has lower resistance?
That's right. A stronger spring is also a better conductor in this model.
Oh, okay, so it's like they're linked.
Exactly, yeah.
The strength and the conductivity.
That's a key connection. And it's this relationship that's really at the heart of why case 9 ends up being so cost-effective.
Okay, so resistance check. Now what about the response force? How do we measure how strong this case 9 setup actually is?
Well, they use this really clever concept called the equivalent spring.
Equivalent spring?
Yeah, basically it lets us simplify multiple springs connected in series or parallel into a single spring with a specific elastic limit.
So it's like even though we have these multiple springs all connected in different ways, we can treat them as if they were just one single spring.
Exactly. It makes calculating the response force much simpler.
Oh, I see. So for those 3 springs that are connected in series and parallel, we can figure out their combined elastic limit, like how much they can stretch together before they permanently deform.
Exactly. The paper calls this combined limit C234.
C234, okay.
And the total response force of the system, basically the maximum stress it can handle, depends on how C234 compares to the elastic limit of that 4th spring, C1.
Right, the one that's connected to them in series.
If C1 is smaller than C234, then the system's response force is limited by C1. It's like the weakest link in a chain.
Right, if that one gives out, the whole thing breaks.
Exactly. So the researchers were really focused on figuring out how to balance these different elastic limits to get the strongest possible system.
But they weren't just going for the strongest system, right? They also wanted it to be a good conductor.
Oh, you're absolutely right. It had to be both strong and conductive. And that's where this idea of a multifunctional performance constraint comes in.
They had that formula, I think, to balance those 2 things.
Yeah, they did. The formula is FRC equals 0.2 times FC plus 0.1 times RC. So FR represents the performance metric, F is the response force, and R is the resistance.
And that formula essentially makes sure the final design isn't just strong, but it's also a decent conductor.
Right. They set a specific performance threshold for FR, so the system has to meet certain criteria for both strength and conductivity.
Okay, I see. So they have this formula to balance strength and conductivity. But how do they actually find the best values for each spring's elastic limit? It seems like a really complex puzzle with 4 different variables to juggle.
And that's where things get really ingenious. They use inequalities to cut through the complexity.
Inequalities.
Yeah, basically they analyze different scenarios based on which springs reach their elastic limits first. Remember, when a spring hits its limit, it's like it no longer contributes to the overall strength.
Right, it's broken.
Exactly. So by looking at all the different combinations of potential weakest links, they came up with a set of inequalities that relate the elastic limits of the springs, C1, C2, C3, and C4, to the response force, FC.
So they're kind of breaking down the problem based on which spring might be the weakest link.
Exactly. And these inequalities become like boundaries. They define a feasible region, basically all the possible values for C1, C2, C3, and C4 that actually satisfy the constraints of the problem.
So any combination within this region is a potential solution, but only one combination will have the lowest cost.
Exactly, and that's where the cost function comes in.
Right, because the whole goal is to minimize cost.
Absolutely, that's the objective. The cost function, represented by CC, equals C1 plus C2 plus C3 plus C4, simply adds up the elastic limits of all 4 springs, which gives us a good estimate of the material cost.
So it's like searching for the point within that feasible region, where the sum of all the coordinates is the smallest.
A perfect analogy. Now, here's the brilliance of their dimension reduction technique. They manipulate those inequalities that we talked about, and they manage to eliminate 2 of the variables.
Wait, eliminate variables? How do they do that without changing the problem?
It's a strategic move. They essentially prove that, for case 9, the optimal solution has to lie on a specific boundary of the feasible region, where 2 of the variables are equal.
Okay.
Specifically, C2 must equal C3 in the optimal solution.
So they're using the inequalities to simplify the problem, but in a way that guarantees they're still finding the best possible solution.
Exactly. They're not just randomly getting rid of variables, they're doing it very strategically based on the structure of the problem. And by doing that, they transform what was a 4-dimensional problem into a much more manageable 2-dimensional problem.
Oh, okay. Which is how they can then use a graph to visualize the solution.
Exactly. They plot the cost function and the performance constraint on a graph with C1 and C2 as the axes. That feasible region we were talking about, that becomes the area on the graph where those constraint inequalities hold true.
And they just look for the point in that region that gives them the lowest cost.
Precisely. The optimal solution is literally the point within that feasible region that sits on the lowest cost contour line. It's kind of like a treasure map, where the treasure is the lowest cost and the map guides you to the exact spot.
So what did their treasure map reveal for case 9? What were those optimal values?
They found that C1 equals 0.75 and C2 is approximately 0.577. And because they'd already proven that C3 equals C2 in the optimal solution, C3 is also approximately 0.577.
Okay.
And then, using a specific inequality for case 9, which states that C1 is less than or equal to C2 plus C4, they determined that C4 is approximately 0.173.
So they used the math to simplify the problem, visuals to find the solution, and then went back to the inequalities to figure out the remaining values.
Exactly. It's a really elegant process.
So what's the minimum cost for case 9 with these specific values?
The minimum cost C comes out to be approximately 2.077. But remember, they still had to prove that none of the other 9 cases could beat this cost.
Right, they can't just assume case 9 is the winner. They need to show why the other contenders fall short. How do they go about that?
They use a similar strategy, reducing those variables and really looking at those inequalities to systematically rule out the other cases. It's like a detective meticulously eliminating suspects.
So they go through this whole process for each of the other 9 cases to prove that none of them can actually beat that cost of 2.077.
That's exactly right. They don't have to actually find the precise optimal solution for each case. They just need to show that there's no solution within those constraints that can do better than case 9.
That makes sense. Saves them a lot of time and effort, right?
Definitely. It's a really efficient approach. And they do this by using a combination of mathematical analysis and some pretty insightful graphical visualization. In some cases, they can reduce the problem down to a single variable.
Oh, okay.
And that makes it really clear that the cost is always going to exceed 2.077.
Like those one-dimensional graphs, right?
Precisely. But then for other cases, they might still have a 2-variable problem.
Okay.
But by carefully plotting the constraints and the cost function on a graph, they can see visually that no solution within that feasible region can achieve a lower cost than case 9.
So they're kind of combining the precision of math with that visual intuition.
Yeah, exactly. It's a powerful combination.
So they went through each of the 9 remaining cases used this approach to demonstrate why case 9 really is the best.
Yes, they did a very thorough job.
It's pretty impressive. And, one of the things that really stands out to me is how they were able to reduce the complexity of these problems. It makes this whole idea of optimization seem a lot less daunting,
That's one of the amazing things about math. You can take a problem that seems really complicated and you can break it down into smaller, more manageable pieces.
Right.
And in this case, they were able to find a really elegant solution.
I'm also really impressed with how they went that extra mile. They didn't just find the best solution, but they also proved very rigorously that it was the best by systematically eliminating all the other possibilities.
That's what good science is all about.
Yeah.
Right? It's not enough to just present a result.
Right.
You have to be able to justify it. You need the evidence, you need to have strong support, and you need to show why it's the best possible solution.
Yeah.
And this paper does an excellent job of that.
It really does. And, we've focused a lot on proving that case 9 is the best, but I'd love to, actually dig into the mathematical details a bit more.
Sure.
Specifically, how they derive those optimal values for C1, C2, C3, and C4 for that specific case. Let's really get into the weeds a little bit.
Absolutely. Let's do it. It all starts with really understanding the constraints of the problem. So remember, the researchers were trying to minimize the cost of making these lattice spring systems, but they also wanted to make sure that they met a certain performance threshold, both in terms of strength and electrical conductivity.
Right, that multifunctional performance constraint.
Exactly. And that formula, FRC, equals 0.2 times FC plus 0.1 times RC, really sets the lower limit for the system's performance. It basically says that this combined value, 0.2 times the response force plus 0.1 times the resistance, has to be greater than or equal to 0.5.
Right.
And that makes sure that the final design has enough strength and also conducts electricity well enough.
Okay. And they also had a separate constraint just for the response force itself, right?
Oh, you're right. They said that the response force, FSC, has to be greater than or equal to 0.75. So that guarantees the system can withstand at least a minimum level of stress.
Okay, so we have these two main constraints, but how do they actually lead to finding the values for C1, C2, C3, and C4?
That's where the inequalities come in.
Yeah.
Remember, they looked at different scenarios based on which springs reach their elastic limits first. So when a spring hits its elastic limit, it can't contribute to the overall strength anymore. It's like that weakest link in a chain.
Right.
So by considering all these different combinations of potential weakest links, they came up with a set of inequalities. And these inequalities relate the elastic limits of the springs, C1, C2, C3, and C4, to the response force, FC.
So they're looking at which spring is most likely to break first, essentially.
Exactly. And that helps them define those boundaries, that feasible region, where all the possible values for the springs actually make sense within the problem's constraints.
And then they have to find the combination of values within that region that results in the lowest cost.
Exactly. And that's where the cost function takes center stage. We want to minimize the cost, right? And our cost function, CC equals C1 plus C2 plus C3 plus C4, just adds up the elastic limits of all those springs. It's a simple way to represent the material cost.
So they're essentially searching within this feasible region for the point where the sum of all those values, those coordinates, is the absolute smallest.
A perfect analogy. Now, this is where things get really interesting.
Okay.
They use a really clever trick. They call it dimension reduction. They manipulate those inequalities we talked about, and they manage to get rid of two of the variables.
Wait, get rid of variables. How do they do that?
It sounds kind of counterintuitive, but they prove that for case 9, the optimal solution has to lie on a specific boundary of that feasible region. And on this boundary, two of the variables are equal. Specifically, they show that C2 has to be equal to C3 in the optimal solution.
So they're basically simplifying the problem.
Exactly.
But in a way that still guarantees they're getting the absolute best answer.
Precisely. And by doing this, they transform a 4-dimensional problem into a much simpler 2-dimensional problem.
Oh, wow.
And that's what allows them to use a graph to find the optimal solution.
Because now they only have two variables to plot.
Exactly. They can plot the cost function and the performance constraint on a graph where the axes are C1 and C2. And the feasible region becomes this area on the graph where those constraint inequalities are true.
So it's like a visual representation of all the possible solutions that meet those criteria.
Exactly. And then the optimal solution, the point with the lowest cost, is literally the point in that region that sits on the lowest cost contour line. It's kind of like a treasure map, where the treasure is the lowest cost and the map guides you right to it.
Okay. So what treasure did they find for case 9?
They found that C1 equals 0.75 and C2 is approximately 0.577.
Okay.
And since they already proved that C3 is equal to C2 in the optimal solution, C3 is also approximately 0.577. Then, using one of the inequalities for case 9, they figured out that C4 is approximately 0.173.
Wow. So they used the math to streamline the problem. They used visuals to actually pinpoint the solution. And then they went back to those inequalities to work out those remaining values.
It's really quite elegant.
It is. It's a really cool approach. Now, I remember you mentioned something called Proposition 1 earlier, and it seems pretty crucial to making sure this whole shortcut of theirs actually works. Can we dig into that proof a little bit? I'm really curious about how they connect that simplified 2-variable problem to the original one with 4 variables.
Absolutely. Let's unpack Proposition 1. What this proposition does is it formally proves that the solution you get from that simplified 2-variable problem actually gives you the solution to the complete 4-variable problem.
Yeah.
It's the link that validates their whole dimension reduction strategy.
So without that proof, we wouldn't really know for sure if the optimal solution they found on the graph is actually the optimal solution for the original problem.
Exactly. It bridges that gap between the simplified and the full problem.
Okay.
So how do they do it? They start by assuming they have a solution to the reduced problem, which we'll call C1, C2. And this solution is a set of values for C1 and C2 that minimizes the cost function, which we'll denote as C tilde C1, C2, while still satisfying the constraints of that reduced problem.
So they're basically saying, let's assume we've already found the best values for C1 and C2 in that simplified problem.
Exactly. Now, the proof needs to show that when you take those values and plug them back into the original 4-variable problem, they actually give you the optimal solution for C1, C2, C3, and C4. It's like connecting the dots between the simple and the complex.
So showing that the best answer in the simplified world is also the best answer in the original, more complicated world.
Precisely. And they do this by building a chain of inequalities. First, they show that the cost function for the reduced problem, that C tilde, C1, C2, is always less than or equal to the cost function for the complete problem, which we'll call CC1, C2, C3, C4.
Okay.
And this is true for any set of values that satisfy the constraints.
So the cost in the simplified problem is basically setting a lower limit for the cost in the original problem.
That's a great way to put it. And this is really important because it means that if you find the absolute lowest cost in the reduced problem, you've automatically found the lowest possible cost in the complete problem as well.
Oh, I see. So finding the minimum in that simpler version guarantees that you've also found the minimum for the original, more complex problem.
Exactly. That's the key.
Hmm.
The next step is to show that when you plug that optimal solution to the reduced problem, that C1, C2, back into the complete problem, it gives you the same cost as what you calculated in the reduced problem.
Okay.
So they're basically demonstrating that the best solution in the simple world is also a valid and optimal solution in the original, more complex world.
That's pretty clever.
It is. By putting those two pieces together, the fact that the reduced cost is a lower bound, and the fact that the optimal solution to the reduced problem achieves that lower bound when you apply it to the complete problem, they prove that solving the reduced problem is actually the same as solving the complete problem.
Wow, they basically built this bridge between the two problems, showing that optimizing in the simpler version is mathematically the same as optimizing in the original one.
Exactly. And that's what makes their approach so powerful.
Proposition 1 really is the glue that holds their whole method together.
Absolutely. It gives that mathematical rigor to their dimension reduction strategy. It assures us that those optimal values for C1 and C2 that they found in that simplified problem are indeed the optimal values for the complete 4-variable problem.
It's impressive how much care they took to really prove every step of their approach.
It is. It's a great example of how a well-executed mathematical analysis can lead to a really deep understanding and result in practical solutions to real-world problems.
This has been so insightful. We've really gone deep into their methodology, from setting those constraints and simplifying the problem to actually finding that solution and proving that it's the best one.
It really highlights the power of combining mathematical analysis with engineering intuition.
Absolutely. So what's next? What other insights await us?
Well, we've spent a lot of time with case 9.
We have.
But you're right, there were 10 cases total.
Yeah, how did they actually rule out the other 9?
Yeah.
To prove that case 9 was really the most cost-effective.
Well, they used that same systematic approach we've been talking about.
Okay.
Reducing the variables, using those inequalities to analyze each case and show why it couldn't be better than case 9.
So for each of those other cases, they went through that whole process.
It did.
Defining the inequalities, simplifying, and then checking if any solution could actually beat that 2.077 cost. Seems like a lot of work.
It is thorough, but they didn't have to find the exact optimal solution for each of those 9 cases.
Oh, okay.
They just had to prove that none of them could be better than case 9.
Right, so it's more about disproving possibilities than actually solving each one completely.
Exactly.
That's efficient.
Very much so.
So what did they actually do to eliminate those other cases?
Well, they used a combination of mathematical analysis, and they used those graphs to visualize the problem.
Okay.
And sometimes they could simplify the problem down to just one variable.
Yep.
And that made it really obvious that the cost would always be more than 2.077.
So they could use those simple one-dimensional graphs to quickly rule out those cases.
Exactly. But for some of the other cases, they might still have a 2-variable problem to deal with.
Oh, right.
But by plotting those constraints, and the cost function on the graph, they could visually see that there was no solution within that feasible region that could possibly beat case 9.
So they used that visual intuition, but backed it up with a mathematical analysis.
Yes, that's right.
It's a really neat approach. So they systematically went through all 9 cases, used those techniques to show why case 9 really is the best.
They did, and it really highlights their thoroughness.
It does. One thing I'm really struck by is how much effort they put into not just finding the solution, but proving that it was actually the optimal one, eliminating all those other possibilities.
That's really important.
Yeah.
It's not enough to just say, here's the answer. You have to be able to back it up. You need the evidence. You need that solid mathematical proof.
It's really impressive.
It is. It shows a real commitment to scientific rigor.
This whole deep dive has been really eye-opening.
I'm glad.
We've gone from unpacking the problem, understanding those constraints, to actually seeing how they use these really clever techniques to find and validate that best possible solution.
It's been a journey.
It has.
And it's been great to see how these researchers combined those mathematical tools with real engineering ingenuity to solve a really challenging problem.
Absolutely. But, as we're wrapping up, I'm thinking of the bigger picture. They focused on this one-dimensional model, right, with all the springs along the line.
Right.
What if you wanted to apply these concepts to something more complex, like a 2- or 3-dimensional structure?
That's a great question. And it's a natural next step to think about.
Yeah.
Moving into multiple dimensions definitely makes things more complex. Can you imagine the interactions between those springs in a 3-dimensional lattice? That would be a lot to analyze and optimize.
Oh, yeah. The possibilities just explode, don't they?
They do, but the fundamental principles would still apply. Even though the complexity ramps up, those core ideas of optimization, the constraint analysis, the mathematical proofs, those are all still crucial.
So it's like having this really powerful toolkit that can be adapted to tackle even bigger problems.
Exactly.
That's really cool.
Yeah.
We might need to consider more factors too, right?
Yeah, you're right. It's not just strength and conductivity anymore. You might have to think about things like the weight of the structure, how it holds up to heat or other environmental conditions,
Right.
how flexible or rigid it needs to be.
So it becomes a multifaceted problem with all these different performance characteristics and design considerations.
It does, and that's where the real creativity and engineering comes in. Defining those objectives, identifying the constraints, and then using math to find the best possible solution within that really complex landscape. That's what engineering design is all about.
This deep dive has been amazing. We've not only learned about lattice-spring systems, but also about how we can use mathematical thinking to solve real engineering challenges. It's inspiring to see these abstract concepts applied to real-world problems.
I'm glad you enjoyed it.
I did. Any parting words of wisdom before we sign off?
Just this. Never underestimate the power of a well-defined problem and the elegance of a really solid mathematical solution. Even the most complicated challenges can be solved if you have the right tools, a little bit of creativity, and a willingness to really dig into the math.
That's a great takeaway. Thank you so much for joining us on this deep dive. It's been a pleasure exploring these ideas with you.
The pleasure was all mine.
And to you, our listeners, thank you for tuning in.
Yes, thanks for listening.
We hope you found this as fascinating as we did. Until next time, keep exploring, keep questioning, and keep diving deep. Hey everyone, ready for another deep dive?
Always ready to explore some cool research.
Well, today we're looking at a paper that's a mix of material science, engineering, and math.
Sounds like a fun combination.
It's called a dimension reduction procedure for the design of lattice-spring systems with minimal fabrication cost and required multifunctional properties.
Okay, that's a mouthful.
I know, right? It was originally published in August 2017, but it was updated just this past March.
So pretty recent stuff.
Yeah. Basically, the researchers figured out how to design these super strong and cost-effective lattice-spring systems.
And how did they do that?
Through topology optimization. It's all about using math to find the best possible design for a specific purpose.
Gotcha. So like building the perfect material.
Exactly. But instead of, bricks and mortar, we're talking about equations and variables. The goal is to find that sweet spot where you maximize strength and conductivity without breaking the bank.
Strength and conductivity.
Yeah. So this paper focuses on elastoplastic materials. Elastoplastic. It means they can stretch and bend like elastic, but they also have a point where they permanently deform, like plastic.
Okay, makes sense. So what kind of materials are we talking about here?
They look specifically at lattice spring models. Imagine tiny interconnected springs that can also conduct electricity.
So we're talking about materials that need to be strong A&D good conductors.
Exactly. And finding the optimal design for those materials can get pretty complex. Think about juggling a bunch of equations, each one representing a different factor like strength, conductivity, cost.
Yeah, that sounds like a headache.
Right. It's like solving a multi-dimensional puzzle.
So how did they even start tackling this?
Well, they simplified things. They focus on models with just 4 springs.
4 springs? That seems overly simple.
Right. But previous research showed that in a lot of optimal designs, some springs get eliminated entirely.
Huh, interesting. So less is more, I guess.
Sometimes. But even with just 4 springs, there are still a ton of ways to arrange them.
That's true. So how did they figure out which arrangement was best?
That's where Table 1 of the paper comes in. It lists all 10 possible ways to arrange 4 springs on these one-dimensional nodes. Each arrangement is labeled as a different case, which they analyze one by one.
So it's like they made a blueprint for every possible combination.
Exactly. And they had some ground rules in mind, like minimum requirements for the material's strength, which they called response force, and the overall performance, meaning how well it combines strength and conductivity.
So they weren't just randomly testing stuff out. They had a specific target in mind.
Right. They even expressed those requirements as specific equations in the paper.
Interesting. It's like an engineering challenge.
Totally. So they started analyzing each case. And this one case, case 9, kept popping up as a potential winner.
Really? What's so special about case 9?
Well, for starters, the way the springs are arranged is pretty unique. In case 9, you have 2 springs connected in series, and then that pair is connected in parallel with the other 2 springs.
Well, hold on. I'm trying to picture this. It's like 2 mini chains of springs running side by side, right?
Yeah, kind of.
And then those chains are linked together.
Yeah, exactly.
Interesting. So how does that affect the whole system?
Well, it has some interesting implications for how the system behaves. Like, remember the concept of an equivalent spring we talked about earlier?
Yeah, that's the overall stiffness of the system, right?
Exactly. So in case 9, we can actually treat those 2 springs in series as one single spring, and that makes a big difference.
So it's like the whole system is simplified because those 2 springs act as one.
Right. We can figure out the elastic limit of that combined spring, which will be the lower limit of the 2 individual springs, kind of like a chain being only as strong as its weakest link.
Gotcha. So this equivalent spring, which represents those 2 springs in the series, is connected in parallel with the other 2 springs. That parallel connection must be what makes the system strong, right?
Yeah, it's a big part of it. But the researchers also had to analyze how the forces would be distributed within the whole system, considering which springs might reach their elastic limits first. gets pretty complicated.
I bet. So they had to look at a bunch of different scenarios.
They did, and this is where their clever dimension reduction technique comes in. They were able to simplify the problem from 4 variables down to just 2.
Wait, what? How did they do that?
It's some serious magic, but basically, they recognized relationships between certain variables which allowed them to reduce the complexity.
Huh. Sounds pretty impressive. But how does that apply specifically to case 9?
Well, in case 9, that dimension reduction lets them express the cost and performance of the material using just the strengths of 2 of the springs.
Ah, so it simplifies things even further. They can visualize it on a 2-dimensional graph.
You
right?
got it. And what those graphs reveal is that case 9 can achieve the required strength and conductivity with a lower combined value of those 2 spring strengths than any other case.
So because the strength of a spring basically translates to material cost, that means case 9 is the most cost-effective option.
Exactly. It's like they found the holy grail of material design, high-performance A&D, low cost.
That's incredible. But did they just assume case 9 was the best, or did they actually compare it to the other cases?
Oh, they didn't stop there. They went back and rigorously analyzed all the other cases to prove that none of them could match case 9's performance at a lower cost.
Wow. So they went through each of those other 9 cases one by one.
Yep. And each case had its own set of challenges and calculations.
Okay, now I'm really curious to see how they ruled out those other cases.
Let's dive into those other cases and see what they found. All right, so let's break down these other cases. Starting with case 1, how did the researchers approach the analysis?
Well, case 1 had a totally different arrangement of the 4 springs, which meant using a different formula for calculating the electrical resistance.
Oh, so even with the same number of springs, the arrangement really impacts things.
Absolutely. The way they're connected in series and parallel makes a big difference in how their individual strengths contribute to the overall resistance. And on top of that, they also had to analyze the response force, like which springs might hit their elastic limits first.
I can imagine that gets pretty complex with all the different combinations.
Yeah, it leads to all these subcases, each with its own set of equations.
So they had to analyze each of those subcases separately?
Yeah, and simplify those equations to make the comparison to case 9 more straightforward.
So they were trying to find a way to directly compare the performance and cost of each case to case 9, right?
Exactly. And with case 1, they were able to boil it down to formulas with just one variable.
Ah, so back to those handy 2-dimensional graphs.
You got it. And once they plotted everything out, it was clear that case 1 just couldn't compete with case 9. No matter how you tweaked the spring strengths, it just couldn't achieve the same level of performance at a lower cost.
So case 1 was out. What about case 2?
Case 2 turned out to be a bit simpler. The resistance calculation was just the sum of the reciprocals of all 4 spring strengths. No complex fractions or anything.
Straightforward addition, huh?
Yep. And they could analyze the response force using a single variable too, which made comparing it to case 9 super direct. But again, no matter how they adjusted things, case 2 just couldn't match case 9's cost effectiveness.
All right, so 2 down, and case 9 is still looking strong. Let's move on to case 3.
Case 3 had a slightly more complicated resistance formula, a bit more intricate than case 2, but the researchers followed their same systematic approach. Break down the analysis based on which springs reach their limits first, simplify the equations, and visualize the results.
So it seems like each case has its own unique challenges when it comes to calculating the resistance, but in the end, they all get compared back to case 9.
Exactly. And case 3, well, it just couldn't reach the same performance level as case 9 without costing more, just like the others.
Okay, case 9 is still holding steady. What about case 4?
Case 4 got a bit more interesting. The resistance formula was a mix of reciprocals and direct values of the spring strength, so a little more complicated than the previous ones. They needed 2 variables to express the multifunctional performance and cost.
So back to those 2-dimensional maps for visualizing the solution space.
Exactly. But even with 2 variables, the result was the same. Case 4 just couldn't find that magic combination of values to beat case 9 in terms of both cost and performance.
Case 9 is a tough one to beat. So how did case 5 compare?
Case 5 was pretty similar to case 4, with a more complex resistance formula and needing 2 variables for the analysis. They simplified everything, visualized it, but in the end, same story.
Another win for case 9 is really dominating this competition.
It is. And, it really shows you how carefully the researchers analyzed each case. They really wanted to be sure about case 9's superiority.
So we're halfway through the cases, 5 down and 5 to go. I'm really curious to see if any of the remaining ones can challenge Case 9.
Yeah, let's keep exploring and see what we find.
All right, back for the second half of our Case 9 showdown. Let's see what the remaining cases have in store. Where do we start?
Case 6, this one was a bit trickier.
Okay. How
Yeah.
so?
They had to split the analysis into two subcases based on which springs reach their elastic limits first. Kind of like we saw with Case 1, where the order the springs hit their limit changed how the system behaved.
Right, so even with this simplified system, the way those springs interact can get pretty complex.
Yeah, for sure. But the researchers, they simplified the equations for both of those subcases, got everything down to formulas with just one variable, which made comparing it to Case 9 a lot easier.
And I'm guessing the outcome was the same. Case 9 still outperformed.
Yep, Case 6 couldn't match the performance of Case 9 without being more expensive.
All right, another win for Case 9. What about Case 7?
Case 7 had two subcases as well, this time based on the combined strength of certain pairs of springs.
So like a different way of slicing the problem.
Yeah, exactly. But the researchers, they handled it the same way, simplified the formulas, visualized the results, and compared it all back to Case 9.
It's pretty impressive how they systematically analyzed each of these cases.
It really is.
So what happened with Case 7?
Same result. Couldn't beat Case 9. Even with those subcases, it just wasn't as cost-effective.
2 more to go. On to Case 8. Did it shake things up?
Case 8, actually, it was the simplest of all the cases. The resistance was easy to calculate, and they could analyze the whole thing with just one variable. No subcases or anything.
Wow, that's refreshing after all those complex ones. But I bet Case 9 still won, right?
Haha, you got it. Case 8 just couldn't match the performance and cost-effectiveness of Case 9.
All right, last one. Case 10, the final showdown. Did it give Case 9 any trouble?
It was a bit more work for this one. I had to deal with two subcases again, and the analysis was a bit more involved. But, they managed to simplify the formulas, visualize the results.
Drum roll, please.
Case 9 still came out on top.
Of course it did.
Yeah.
After all that, after analyzing every single case, Case 9 is still the champion.
Yeah. It's the most cost-effective design that could still achieve the required performance for both strength and conductivity.
So let's revisit what makes Case 9 so special one last time. Why does it perform so well?
It all comes down to how those 4 springs are arranged, remember. 2 springs in series, kind of like a mini chain, and then that chain connected in parallel with the other 2 springs.
Right, that's how we get the equivalent spring.
Exactly. And because of that setup, we can simplify the analysis, figure out how the whole system behaves under stress. They had to consider different scenarios too, like which springs would hit their limits first.
And they use that dimension reduction trick to make the math more manageable.
Right, and they could visualize the whole thing on a 2-dimensional graph. That's how they saw that Case 9 hit that sweet spot, high performance, lowest possible cost.
It's like finding that perfect balance, like the ideal recipe.
I like that. And it's not just about these tiny spring systems. This research could change how we design all sorts of materials in the future.
It's amazing to think that analyzing these 4 little springs can have such a big impact.
It is. Really shows the power of fundamental research, how it can lead to amazing things.
Well, this has been a wild ride through the world of lattice-spring systems. We saw some serious math, clever shortcuts, and in the end, Case 9 reigns supreme.
Absolutely.
Thanks for joining us on this deep dive. We'll catch you next time.